izin Bu Dona. Berarti
Oh ya,
nggak ada pembukaannya.
ya nggak ada. Jadi langsung Walter aja.
Oke. Good morning, everyone. Welcome to our event, Global Seismology Training Course 2025. This training will be held for 2 days, for today and tomorrow, 19 and 20 March of 2025. Before we start, I will introduce myself. My name is Rico from BMKG, from Human Resource Development of Center of MKG, and will be your moderator for today's event. We are honored. No, not yet. And because Dr. Nelly is cool, maybe we can move to our first session. And
Kurang
we
keras
have
suaranya tuh, Riko.
Oh,
Iya kok suaranya kencengin dulu
Suaranya
kok.
nggak keras. Bener kan, Mbak Don?
Heeh.
We cannot hear your voice.
yuk cek. Kalau sekarang Bu.
Dah, lumayan.
Okay. We honor to esteemed speaker from BMKG and USGS joining us virtually. To officially open the event, we invite a representative from BMKG, Dr. Nelly Frodiariama, Head Deputy of
Dia
Geophysics
pakai
for BMKG.
pembukaan.
How was? Sorry.
I think we can go ahead. I just
Oh.
want to thank you for all the speakers, especially from USGS and also from our
Okay, I see.
yeah.
Sorry, Dr. Nelly. Then, okay, we our session. We have Dr. Walter Mooney from USGS, who will introduce the purpose of scope of this training. Please welcome Dr. Mooney. Time is yours.
Okay, I will get started. I just need to show my PowerPoint. Thank you very much for your introduction. So is my voice clear? Everyone can hear? Okay?
Yes. Okay. Walter.
Yes, sir.
So,
Very clear.
I'm glad to know that. Well, we're looking forward to today's training course. You know, we've had about more than a dozen of these training courses online, and also training courses in person. So we have a long tradition. Today's training course, the topic was selected by BMKG to focus on global seismology, because some of you have completed some training in Japan recently that touched on this topic. And of course, it's something of interest to all of us. So we will be meeting for 2 days and continuing a long tradition. I want to acknowledge the organization and approval of the course from some of the leaders at BMKG. Of course, your Director General Di Corita, and the Deputy Head of Geophysics, Brunelli, and the new Acting Official Head of Center of Human Resources, Adit, who is also here, I believe. So it's because of the positive reaction and support of these training courses that we're able to go forward. So we have a very interesting morning for you today. The first speaker will be from USGS, the National Earthquake Information Center, Dr. Harley Benz, and he'll talk about global seismology and particularly big earthquakes. Then we're going to look in depth at the properties of Indonesia, the crustal properties, and Dr. Ying Zhang, who is a USGS postdoc, will show her processing of some of your seismic stations to get the crustal structure of Indonesia. Of course, we need this to locate earthquakes. And then Ulfa is going to talk about assessment of, I'm going to have to close this. Hold on a second. Oh, wait a minute. I think I stopped my share. Let me come back to my PowerPoint. Okay. Oh, that's day 2. I need to go back. Okay. And John Bari will talk to us about Unix basic operating systems. They're all very important topics. By the way, is my screen showing again now? Can you see my screen?
Yes.
Yes.
Okay, good. On day 2, we have 5 talks, more about receiver functions from Dr. Zhang. Mohammed Akkadi will talk about digital filtering. And then Yosef will have a very important talk on hypercenter determination, which of course is very important. We will talk about, USGS speaker will talk about earthquake ground motions, and then Reinhard will talk about moment tensors. So as you can see, we have a very broad range of topics, and we'll cover each of these with some great care. Now, I notice a lot of new faces. Many of you have not participated in a training course before, so I just want to say welcome. We're glad that you're here. And without your participation, the training course, of course, would not be as interesting. And we're looking forward to your questions. I'll ask the first few questions to get the ball rolling, as the usual way it works with these courses. But I want everyone to feel free to ask any question they like, and even if it seems to be too simple a question, don't be afraid to do that. So we have just 2 days and 2 mornings. Give you your afternoon free. And now I'll turn it back to Rico, who will introduce the first speaker. Thank you very much.
Thank you, Dr. Walter. Then, okay, before we start, I just wanted to inform you, Mr. Adit Warman cannot join with us virtually because he has an important meeting, and he will join with us for tomorrow in the second days. Okay, thank you, Dr. Muni. Then we move to on our next session on global seismology. It is my pleasure to introduce you, Dr. Harley Benz from USGS, who will share his insight on this important topic. Please welcome Dr. Benz. Time is yours.
Okay, let me make sure that, can you hear me?
Yeah,
Yes,
very
clearly.
clearly.
Okay, good. So I've been asked to talk about big earthquake monitoring by the USGS. And so I'm going to provide a little bit of background on the National Earthquake Information Center here in Golden, Colorado. And then I'll go on to talk about how we think about big earthquakes, where they occur, and how we model them. But I start with this slide. In the early part of the winter, we were honored to have 3 of your colleagues from BKMG visiting NEIC. And when you walk into the operations area of NEIC, the first thing you see is 2 chairs and a potted plant shown here. And I think it was somewhat underwhelming for our guests from BMKG. But in fact, this is the new reality of NEIC. Everything is so highly automated that we don't really have an operations room. Everything's done very fast and high speed. And so this is the first view you actually get of NEIC. But because people complain, we actually put in a big screen down the hallway. But in fact, this is never used. It's only used for visitors. We turn it on when we have visitors, and when visitors leave, we turn it off. So everything's done remotely, done in offices and things. And I'll talk a little bit about this as we go. So just some background. So NEIC integrates about 2,300 seismic stations from around the world, from about 140 networks. NEIC is one of the few earthquake monitoring facilities in the world that operates no instruments. We're solely dependent on others to provide the instrumentation. And so, of course, we manage the global seismic network, the national net, and others, but that's done in other offices. And then we're very appreciative, we're very appreciative of BMKG and others for sharing data with us so we can do our mission. So with this data set, we locate about 30,000 earthquakes per year. This is our web interface, which most of you have seen. It's, we have a global monitoring mission. So on a global scale, we locate about every 4.5 and larger worldwide that we can in a year. And like I said, that amounts to about 30,000 earthquakes. If you go to an individual event, this was the largest in the last couple of years, largest event in Indonesia. It was a 7.1 off the west coast of Sumatra. And as you well know, we produce a whole variety of products, seismotectonic content, macroseismic information, impact and loss estimates, both from landsliding and ground shaking. But I think I will mostly be talking about some of the modeling we do to get the size of these big earthquakes and why they are important. So I just pulled this off today, just say, here was the last big event in Indonesia in the last couple of years. And it was, it was typical, if you had asked me where it was, I would have told you it was a thrust fault shallow angle thrust, and it was. And I'll talk a little bit about this. Here's an example of the products we produce. I won't go into any detail on most of them, but we provide seismotectonic background on our website. And the reason is, as we all know, that few earthquakes are surprising. We understand the seismotectonic context in which earthquakes occur. So there's a lot of things we know the geology, and we can say a lot about an earthquake just by simply knowing where it is and not knowing much about it. But in addition, we produce information on earthquake shaking. And once you have some level of understanding of shaking, you can then do descriptions of the likely impact, both from the shaking of the earthquakes and from other secondary features like landslides. So we can do earthquake impact both on the felt environment and what might probabilistically happen to produce landslides. Over the last 20 years, since the Sumatra earthquake, 20 plus years, NEIC spent a huge amount of effort and resources into doing is accurate and modeling the source properties of earthquakes, the magnitude, the type of faulting, and the slip distribution, all which become important for impact assessment and for generally understanding earthquake potential. And then we work with tsunami warning centers, and then we deal with aftershock probabilities, and I'll just show an example later of that. So it's our monitoring. So the NEIC's major focus, and it hasn't really changed much over the years, but it's always all of the people working in NEIC, particularly from a research point of view, are trying to operationally, we're trying to go faster and be more accurate. And that doesn't matter whether it's the magnitude, the location, or the estimates of impact, economic loss, fatalities, and things like that. And to be able to do this, to go faster, to go more accurate, we're starting to use more of the cloud, using algorithms, moving our algorithms as to web services, and then heavily leveraging AI type applications. And so all of this, so we actually do everything from scenario earthquakes, trying to understand what a future earthquake might look like in different places, doing the event detection and reporting, which happens in tens of seconds to a couple of minutes. Impact products come a few minutes later. We put everything on the web, and then we do much more sophisticated modeling, source modeling, and things like that. Kinematics of the rupture, which happened within an hour to 2 hours. And then ultimately the post-earthquake within hours to days to weeks, we do seismotectonic characterization, impact assessments, and things like that, and to try and understand better that earthquake and what does that earthquake or its associated aftershocks, what is the implications of these for future earthquakes? Okay, so this is basically what NEIC does. Now, to get on to the big earthquake part of the problem, so where do the big earthquakes occur? And this simple map shows the major plate boundaries. And the subduction zones, the major subduction zones are all shown outlined in the heavy black lines shown here. So you can see the Pacific Rim, shown here. You can clearly see the, Sumatra, Java, the Indonesian subduction zone, and you can see subduction, along the Himalayan front and a few other places. And then, of course, down, New Zealand, Tonga, Fiji, and across. So where are the biggest earthquakes occurring? Well, they almost exclusively, I'm talking about the 8, 5, and larger earthquakes. So this is from the beginning of the 20th century. These are the 8.5 and larger earthquakes. They've all occurred on the plate boundaries. It's where we have the highest rates of motions in the world. And the longest bits of real estate or geology on which rupture can occur. And so it's not surprising at all that the largest earthquakes occur at or near the interface, the subduction zone interface. And we know this really well from Sumatra and the series of earthquakes that occurred since 2004, the 2005 and 2012. And those two other earthquakes, the 2005 Simalu and the other one, 2000, these all were a consequence of what happened in 2004. And I'll talk a little bit about. So subduction zones produce the biggest earthquakes in the world. And this is just showing the magnitude 8.5 and larger. And these really big earthquakes, like the Sumatra earthquake, these 9s, take up most of the moment release that's observed since the beginning of the 20th century. And in fact, the 1960 Chile earthquake released about a third of the total seismic energy in the last 100 years. And you can see here from this plot from left to right, it starts in 1900 and goes to near present. And you can see that in that 1906 Ecuador earthquake, which is an 8.8, you can see this step in seismic moment. When you get to 1952 magnitude 9 Kamchatka earthquake, you see a big dramatic step in moment release. The 1960 is the most dramatic. And then it's followed shortly by the 1964 Alaska. And then you see Sumatra, and then the more recent Japan earthquake here. So these magnitude 9s are, they're really big. But it's important to note that while they don't happen very often, and we can't just simply monitor, we at NEIC do everything we can to model the source properties, the mechanisms, the depth, and if we can, the kinematics, the rupture, the directivity of rupture of all 7 and larger, and we're pushing to trying to do it for magnitude 6 and larger, because it's understanding the geometry and how they ruptured has implications or what are likely to be the hazards in the future, particularly the next segment down from these larger events. So, let's just remember that large earthquakes are rare. As you can see on this plot over here, you can see magnitude goes along the bottom axis, and the number of events per year goes along the vertical axis. And we typically have about 1 magnitude 8 per year. less than about 20 magnitude 7s per year. On, I think, average, it's about 15. Some years we may have more, and it's almost always a consequence of aftershocks of a magnitude 8 or 9-ish earthquake. We end up having about 100 plus, 120, 150 magnitude 6s per year globally, and then about 1,000 magnitude 5. And I just said earlier in my talk that NEIC locates about 30,000 earthquakes per year. And at about the magnitude 4 level, there's just over 10,000 earthquakes per year. But NEIC both monitors the globe, and it has a mission within the United States, both the continental US, the Caribbean, and Alaska. And Alaska, like Sumatra, is one of the most seismically active areas. So when you count it up, it's roughly 30,000 earthquakes per year. And we probably don't have the staff, nor should we have the staff, to go down to of Alaska. And so over 100 years, the entire Aleutian front ruptured, or most of it. So it started with a 1906 event, an 8.3 out in the western Aleutians. Then there was a 46 event in the central part of 38, a 46, a 57, 65, and then the big one, the 64. Other than this gap, which is shown in kind of the central eastern part of the Aleutians, which is known as Schumann Gap, the entire Aleutians ruptured in a series of big earthquakes. Okay. So the important thing is that we get a lot of 7s in this area, but they're not contributing significantly to removing this accumulation of strain in the subduction zone. It's really these magnitude 8 and largers that are ones that are failing and releasing most of the strain across the Aleutians. And we see this similar thing in South America and Chile. Here, in 1922, there was an 8.5 in the northern portion of Chile along the trench in the Atacama Desert. And then in 1960, the southern portion of the trench ruptured. And then again in 2010, there was a rupture, the Maui earthquake. And then in 2015, there was another 8.3, and then a smaller one, Iapel, north of here. So much of this trench ruptured in a series of magnitude 8s. And each of one of these ruptures, the kinematics of rupture, the direction in which it ruptured, the displacement, the aftershock zone tells a story of how this subduction zone's behaving and what could potentially happen in the future. There is a gap in this area of Valparaiso and Santiago, and it's an area of worry. Is it just an area of slow slip, or is there accumulation? It's hard to tell just from seismology. We have to start using more and more geodesy to understand these. So one of the things I won't talk about, I'm just going to mention, is there's a lot of effort in NEIC to start better integrating geodesy into what we do. Okay, so I talked about where the big earthquakes occur, but the damaging earthquakes don't seem to correlate with the big earthquakes. And this shows some of the most damaging earthquakes since the beginning of the 20th century. These are typically ones that killed more than 100,000 people, and not all of them are big. The stars are, I think, are shaped based on magnitude. I don't quite remember. No, that's not true. I don't remember what I did this and I can't remember. But the important point here is Sumatra was unusual in that most of the loss of life was from tsunami. Most of the earthquake damage that occurs worldwide are earthquakes that are close to the built environment, and they're close to where the built environment is poorly constructed. So the important thing is earthquakes don't kill people, the buildings kill people. And so some of the largest losses of life from non-tsunami-genic events have been in the Middle East, where construction practices are different in the Iran and others because of the hot and cold climates. Winters can be cold, summers can be very hot. They build very thick domed structures that are very great for insulating temperature or controlling temperature, but they're prone to falling down. And so you have throughout most of Asia, you have you have significant damage from even relatively small earthquakes. And that was the case here in Haiti in 2010. The earthquake occurred almost inside of Port-au-Prince, a major metropolitan area with very poor construction, and it killed a lot of people. So again, the exception was Sumatra, a very large earthquake, but it was tsunami-genic. And so big earthquakes and damaging earthquakes don't go hand in hand. The important thing is we have to model them all now. You can't just model the big ones. Okay, so just a brief background. So the size of an earthquake, which is the physical measure we use as seismic moment, and we can go from seismic moment to magnitude, which we're very comfortable with, but I think the important point here is the size of an earthquake is related to three numbers: the shear modulus of the constitutive properties of the medium, the area that ruptured, and the displacement on it. So if you have a relatively small area, then you have to have more slip to have an equal magnitude for an event that had a large slip area. That would generally have a small slip dimension or slip. It would not have slipped very much. So large area, small slip for an equivalent magnitude. Small area has to have more slip. Okay, and so it becomes really important to try and model these kinematics to understand how much it slipped and over what area. And we can't, and that's just only part of it. We also have to use the aftershocks because they're failing typically on the edges of these patches, and they're small enough that they're not going to accumulate. You won't see them in the distribution of the kinematic models. So just rule of thumb, magnitude 4s have about 1 kilometer of area that slips. 5s are about 10, magnitude 6 on the order of 100 kilometers, 7s, 1,000, and 8s, 10,000. It's generally an order of magnitude, so an 8, whenever I hear about an 8, I'm usually knowing that it's going to have dimensionally lateral dimensions of several hundred kilometers. 7s are going to be tens of kilometers. You just know that, okay, from 30 years of modeling earthquakes. There's few exceptions to this. So this is just a rule of thumb. So you can see takes lots of 4s to equal the same amount of fault area as an 8. So they're not particularly interesting from an understanding the broader scale of seismotectonics, but you still need to monitor them. How do we compute moment? The method that everybody uses now, developed by Hiro Kanamori and others, is the W phase. Up until about 15 years ago, there were two ways of modeling the moment tensor. Using the surface waves, which are shown here in the middle of this plot, which were typically 200 to 400 seconds, but could only be recorded on the best instruments in the world because they could only go to those kinds of periods. So that would be CMT, the classic Harvard CMT. We would use those. The problem is they're surface waves, so it would take 30 minutes to an hour or better to compute a moment magnitude, a mechanism of moment magnitude. The other way was to use the body waves, which are very fast. You could do them in tens of minutes, but they're band limited. They only can see the first part of a long rupture. The frequency content of the body waves is only tens of seconds, not hundreds of seconds and thousands of seconds, which are more representative of the total rupture. But Kanamori and others found out that there was this phase between the P wave and the surface waves in the ocean that had long period characteristics, but it traveled very fast. It was a W phase. So we could use that. And so the W phase it's a mantle phase. It's a complex interference of body waves at very long periods. It rattles around in the mantle. It's fast because it's propagating at mantle type speeds. So it's much faster than the surface wave, but it contains the frequencies, long periods needed to better characterize the total dimensions of the source. And it was described as why it was called the W phase is it was considered analogous to a whispering phase. And the most important thing is the phase could be modeled with normal modes. And what does that mean? Well, that means you could produce Green's functions for these phases. And if you can produce Green's functions, you can take observed data and invert it to get the mechanism in the moment. And so it's ubiquitous now. Excuse me. This is just an example from Sumatra. We didn't use W phase in Sumatra, but by just these two dots on each of these seismograms was the window of the W phase that was used to see what we would have gotten had we used it back in 2004. And you can see we would have had a shallow thrust mechanism to the northeast with a moment magnitude of 9.2. So at NEIC, all magnitude 6 and larger, our preferred mechanism or preferred method for computing moment magnitude and mechanism is W phase. It starts to behave badly below that, but you can use it if you have good data. And we can typically do it somewhere between 7 minutes and 10 minutes typically worldwide. As you can see in this lower chart on the bottom left, and then on the bottom right, you can see that the automatic generally from NEIC is within 0.2 of a magnitude unit of the final. So the important thing is it's very fast, 5 minutes to 10 minutes at most, and it's typically within 0.2 of a magnitude unit of the final moment. So it's very accurate in getting us a mechanism and the moment. That then feeds into our finite fault modeling method, where it's not that dissimilar to inverting the waveforms just to get a mechanism like W phase or body wave. But what we do here is we divide the Earth into little patches shown here in the upper left thing. And in each of these patches, we can assume where the event starts and assume a rupture velocity. So if we have a rupture velocity and where it starts, we can actually invert for the slip on each of these patches, the direction of slip, which is somewhat analogous to the mechanism. And then from the total, we can get the rupture duration. So this is just an extension. So you need to know a location, a moment magnitude, and an orientation of the fault. Once you have that, which we get from a W phase or other methods, we can then we can then characterize this patch, which would be a slip plane that you get from the mechanism, subdivide it up and invert it for the kinematics of rupture. And here's an example from Tohoku. And you can see that the event started at depth and it ruptured upwards, and it had on the order of 650 centimeters of slip up dip. And we can model the body waves. We can model the surface waves, combine them. We can now use GPS and INSAR to help if you happen to have a GPS network nearby. And so you end up with the moment rate function. So in this case, it took about 200 seconds to rupture. And most of the moment release was at about 80 seconds after the initial rupture with some complexity. And that's basically the rupture moving up dip and spreading out across the trench. And so this is a standard method that we now use for modeling all 7 and larger, and we're trying to see if we can get it down to magnitude 6. So I'm coming towards the end. And why do you want to do this? So here is Tohoku. You can see where it slipped up dip from where it initiated and near the trench. And you can see that the trench ruptured to the east of the white line. So you had the outer rise, was starting to slip, and you had large aftershock. You had very few aftershocks in the area that fully slipped. And so the extent of which the interface ruptured is really outlined by the aftershocks here. So you have to get the big events right. You have to put them in the right place, and then you start modeling the aftershocks. And this all goes into trying to understand what are the implications for future earthquake, particularly on the edges of these large ruptures. So we spend a lot of time improving our methods to get down farther and lower in magnitude for these large significant events. GPS is becoming more and more important following Tohoku. The earthquake occurred where the star is, and because the overriding plate slipped, this energy was released, everything went eastward towards the trench with a maximum displacement of about 6 meters. It also went down. Interestingly, now that the trench is starting to relock, things have now gone back up along the coast. So this is just making the point that we can do a lot with seismology, but we have to use geodesy too to understand the behavior of these larger, what happens in these post-earthquake as we redo the earthquake cycle. And so geodesy is becoming important for both modeling the source and understanding the long-term implications. And then earthquakes follow earthquakes, and just show you a couple of examples. Here's an example. This is the end of my talk. This was a 7.1 earthquake, Christchurch earthquake. The initial rupture was actually a thrust fault, but it actually produced strain, and we had most of the rupture was on a strike slip fault just south of where the star was here. It was a magnitude 7. Almost all the moment release was on the strike slip, the east-west blue fault, but in fact there was some thrust faulting north of there. So it initiated and triggered faulting on a bigger fault. That was followed, within a year of a magnitude 6.4 earthquake and its aftershocks shown in the light blue, then followed by, that was in a few months later. And then later on, we had another 6.4, the yellow here, and then it extended offshore. The important thing is it started as a 7, and then through a series of 6 kept propagating east. The 7 here, and I should point out is, one thing I should have pointed out is that we now are doing operational aftershock forecasting of all magnitude 5 or larger earthquakes in the US, and we're doing for 7s and larger worldwide. And because of this, it's based on statistical modeling of the aftershocks. NEIC is being forced to go lower in magnitude to get accurate statistics and be more accurate in the estimate of the magnitude. So both the number of earthquakes and magnitudes were performance at the beginning, location, magnitude, and depth are all being driven now by, or partly being driven by operational aftershock forecasting. And one last slide. So this 771 strike slip event caused, I think, 1 casualty, but it was one of the later events, the 6.3, that caused 181 casualties. 115 were in this building right here that collapsed, and you can see the collapse here. So in a broad scale, what I'm saying is we thought we were done when we thought we were pretty clever when we could routinely do magnitude at 9s, 8s, 7s. Those have actually become quite easy for us to model. But because of the need to understand the nature of the rupture and other things, we're now being forced to go to lower and lower magnitudes to get more detail on these aftershock sequence. So it's a never-ending problem, but I think this gives you a basic idea of what we've been doing at NEIC for the last few years. So big earthquakes. That's it. Any questions? Walter, you want to start?
Thank
Sure.
you.
I do have a question. Can we go to your slide number 10, which was the big earthquake, global distribution of big earthquakes?
Oops. Okay, hold on. I don't know what happened here. Okay, let me go back. Here,
I
I'll
think you went
just
by
start.
it.
Yeah, I'll just start here and then tell me when to stop. Here?
Oh, there we go. Thank you.
Yeah.
So here's my question. It's very simple. We're looking at about 15 very big earthquakes, maybe 20.
Yeah.
I notice a concentration of them in Japan and Alaska, and a very evident lack of big earthquakes in the South Pacific, New Zealand, Kermadec, Tonga,
Yeah.
Solomon Islands, Fiji. What's going on?
Yeah, good question. So, a couple of things, and I also think, since the beginning of the 20th century, the trench in Indonesia is
Right.
an issue. Just point out in the Solomon Islands in the early part of the 20th century, there was a series of magnitude 8.3s. So this is a little bit misleading in that I just showed the 8.5s, the really big guys. So there's a lot, if I plotted eights, you'd see a lot of eights along Indonesia. But it's interesting. So there's been 15 magnitude 8 and larger since the beginning of the 20th century from Papua New Guinea, eastern Papua New Guinea, all the way down to New Zealand. But it just generally doesn't produce magnitude 8.5 and larger. And in fact, the segment of the trench in Vanuatu hasn't produced any eights, and it's one of the most seismically active areas of sevens. So there's what's I think is important is we have to understand how the nature of the locking,
Right.
both how these trenches are being locked or unlocked, the rate at which they're being subducted, and a whole variety of things. Seismology won't tell us this, but geodesy and other things will. But when earthquakes do happen, eights and larger, we have to really dig in detail and look at the aftershocks, the distribution of aftershocks, how far down they go, how do they propagate laterally, what are their mechanisms.
Right.
So we understand the behavior of the rupture.
Well, but since you pointed out the Sunda Trench and the subduction zone near Java, we don't know whether it's capable of a magnitude 8 or greater at this point, or do we
Right.
know? Do we know if it has? What do you think of the subduction at the island at the south of the island of Java? What's the maximum magnitude that we know has occurred?
I think it's in the low eights, could be
Yeah.
high sevens. So it could be, one of the things, if we had infinite resources, I would carpet bomb all the islands, like Japan, if you stand at one GPS site in Japan, you can see the next one if there aren't trees in the way, that they're that close together. But if you were to put super dense network of geodesy, we could see how the trench is behaving as it's subducting. Is it locked or not locked? What areas are slipping more freely versus other? That gives us an idea of dimensionally of what portions are locked, and you can then say, okay, it's several hundred kilometers, that perhaps has a potential of a magnitude 8 or
Right.
thing. You can also look at, the period, the phenomenogenic, how in Alaska, the geologists are digging trenches all over to look at, in previous centuries, tsunami deposits to get an idea of the occurrence of large events in there. And in fact, on this plot between the 64 and the 57 event, or sorry, in the 46 event and the 57 event is the Shumakin Gap. And
Yeah.
people like Rich Briggs and others, they've dug trenches all over in there and they can find no tsunami deposits. So
Oh,
it may not be an area that has a potential for a larger, maybe it just frees,
it's creeping. Yeah.
it's creeping. And you
Okay,
won't
I think we
know
better
this.
let someone else ask a question because I'm the only one who asked. So the floor is open for any question for Harley Benz.
I apologize, this was a very broad talk, but just to give you a feel for how we look at things
Right.
globally.
Very, very good.
Is there a place I should read the questions or?
Okay, thank you. I will read the question. First, this is from Supriyatno. Is it possible to determine the magnitude larger than 7
To do
before?
what?
Is it possible to determine the magnitude larger than 7 before 3 minutes? And the second, how to determine the fast magnitude of slow earthquake for tsunami warning, like Pangandaran earthquake?
So I think that I didn't quite understand data mine. What does that mean? I don't quite know. The other thing is these slow slip earthquakes, they're problematic. But fortunately, with things like W phase and others, if you have a good quality network, you're going to see these slower events. You're going to see it in the very long periods. There was an earthquake. It wasn't particularly big in Nicaragua, but it was a very slow earthquake, and this was in '92. And our classic methods, we couldn't tell that it was slow, and we underestimated the magnitude. And with W phase, we're able to retrospectively go and look, oh yeah, it was this, and we could see that it was an extended slow source. And so these newer methods can help, like W phase, but it's also important. You got to have good quality stations. Just having a broadband doesn't guarantee you'll be able to do these things accurately. You have to have very quiet, high quality broadbands. You don't need them everywhere. You just need some.
Good answer.
Thank you. Okay, Mr. Armansyah, please.
Okay, good morning, everyone. My name is Armansyah. I'm from BMKG Makassar in Sulawesi Island. I have a question to,
Sulawesi?
yeah, from Sulawesi.
Oh, okay. So Eastern Indonesia.
Yeah.
So, okay.
Thank you, Benz, for your presentations. It's a good presentations. I interesting to your presentations in page number 9. You show us the maps of earthquake in the world, like in Ecuador in 1906 with magnitude 8.8, in Sumatra with magnitude 9.1, like in Japan in 2011 with magnitude 9.1. But my questions, what do you think about the many earthquakes with relatively small magnitudes between 4 until 5, but causing significant damage? It's like earthquake in Cianjur in West Java in November 2020 with magnitude 5.6, but it give casualties until 334 peoples, and it causes damage until 54,000 damage to buildings. What's your opinion about this? Thank you.
Yeah, well, I think I have a figure here somewhere here. So, you know, it's all about where the earthquake is, what is the built environment like, the housing, like in the Sinjar earthquake, do you say Sinjar? Is that pronounced properly? The the Java earthquake that killed a lot of people, it was about a magnitude 5-ish earthquake, because I remember. There's a couple of unfortunate aspects about it. One, um, it was small and surprising that what the damage it did, but it was very shallow. Okay, and it was really close to the built environment where people live. We live in buildings, and the buildings fell down. And so this is going to happen. I mean, in the 2003 BAM earthquake in Iran killed 60, 80,000 people. It was a magnitude 6 earthquake. It happened to occur right in town, and it was shallow. And so, you know, we generally don't see a lot of casualties along in South America and the US and Japan and others, because particularly in Chile, they've they've done a lot of work on the building codes. They build very strong buildings since the 1960 event. And so they've had a whole series of eights that they have tsunamis, they have casualties from tsunamis, but they generally don't have that many casualties from collapsed structures because of the effort since the 60s. And that's the same case since San Fernando Valley earthquake in the US of new construction techniques, and Japan's always been well known for that. So it's just unfortunate. Small earthquakes can cause damage, but they have to be really close to the built environment. And there has to be something about the built environment, poor construction, that causes casualties.
Yeah, thank you, Benz. In my opinion, what we need to do is anticipate all potential of earthquake, because small earthquakes will give more damage if the locations close to the city. Thank you.
Just to point out the areas that we worry about for big earthquakes, where in the US, when we talk about global earthquakes and where we're worried about them is, we're worried about an earthquake near New Delhi on the Himalayan front that could do devastating damage to New Delhi, primarily because of just the huge population there. Another area is Tehran is a mega city, and it basically straddles a major fault. Now, the fault may only produce a 7, 6.5 or 7, but given the quality of construction, the dense urban population near the fault, it could be really catastrophic. And then, of course, I don't understand the Sunda Trench at all. And, what's the possibility of a large damaging earthquake impacting, say, Jakarta, if there was a magnitude 8 or larger in along the subduction front in Java? I don't know.
Thank you, Benz. And I'm
Mhm.
really sorry to stop our discussion for this session.
Okay.
Maybe we can more discuss in the next session in the session 5. And after Dr. Zhang presentation, we can do this more discuss. And thank you, Dr. Benz, for your valuable presentation. Now we will continue to the next session. Our next session is on seismic receiver function for Indonesia, presented by Dr. Ying Zhang from USGS. Please join me in welcoming Dr. Zhang. Time is yours.
Okay, thank you. Let me share my screen.
Yes, please.
Okay. Share. Okay. Okay, can you see my screen right now?
Yes, clearly.
Okay, that's nice. Okay, hello everyone, this is Yin Zhang, and I'm so glad to be here to talk about the seismic receiver function in today's training course. Okay, so my outline is as follows. First, I'll talk about the basic concept of receiver function. Next, I'll provide some good and bad examples from Alaska stations about the data quality control. Then I'll talk about some basic concept of HK stacking. It's actually HKAPA, but I usually call it HK. And finally, I'll talk about some applications of receiver functions and the HKAPA stacking in different regions, such as in Indonesia and in Fiji. So we'll talk about those areas tomorrow. So the basic concept of receiver function, it revolves around analyzing the conversions of seismic waves using converted waves, for example, the P converted to S waves or the S wave converted to P waves as they interact with subsurface layers. So in simple term, it focuses on the converted waves when the seismic waves hit the boundaries, such as Moho or the LAB. So let's take P wave receiver function as example. So this is Earth's surface, and we have crust, mantle, and Moho discontinuity, where it has a large velocity contrast. So when an earthquake happens, it releases energy. So the energy travels through the Earth as different kinds of waves, including P waves and S waves. So we're talking about P wave receiver function. So we only focus on the P waves. So in this case, some of the P waves will be transmitted, and these P waves will be recorded on the vertical component. So we call it PP wave or direct P waves. But some of the P waves will be converted into S waves. So we will have these PS conversions recorded on the radial component. So the conversion point right beneath this station is where the conversion happened, or we see the converted waves generated. So these phases can be separated from the incident source by a process called deconvolution to rule out the instrument response and mantle effects. Okay, so what does the receiver function need? First one, seismic waves. It needs body waves, P waves or the S waves. Seismic station, we're gonna have 3 component seismometers. And the most important thing is we want high quality seismograms. So we make sure the traces are clean, make sure they have good signal to noise ratio, and we make sure we have the correct calibration of instrument to avoid some errors. And we're gonna have accurate timing to identify the arrival times for different seismic phases, for the P waves or for the converted S waves. The last one is earthquake source information, including epicentral, depths, origin time, to get accurate calculation of the rate paths. Because when it comes to the receiver functions, the rate paths are really important because they dictate how the seismic waves interact with the Earth layers. And these interactions can show up in the traces when we analyze. Okay, so this figure here shows in the Seismology Olympics, P waves always win the races. So we have time differences between the direct P waves and the converted S waves. We can use a time difference between the direct P and the PS conversion to estimate the depths at which the conversion happened based on the known P wave velocities. So the receiver function are how we measure that time differences. We have 2 common types of receiver function. First one, P receiver function. We use P converted to S waves. Second one is S receiver function. We use S converted to P waves. It can be SH or the SV. So for the P receiver function, so this is the equation for P receiver function. We deconvolve the vertical component from the radial component. for the S receiver function, we deconvolve the radial component from the vertical component. So these are the two common types for receiver function. To sum up, the receiver function are time series, and it shows the relative response of Earth structure right beneath the receiver or near the receiver. It's a very useful tool to measure the discontinuities, such as MOHO or the LAB, right beneath the stations using the converted waves. And the seismometers are 3 components, and earthquakes are seismic earthquakes. So receiver function is easy to implement and is a robust method, especially for the crustal structure in different regions. So after we're gonna do the pre-processing for the raw data. After we removing the instrument response and the mean value and the linear trend, do the general quality control for the traces, we're going to have this rotation process. So this is the surface, and this is interface. This is transmitted P waves recorded on the D component. And these are the converted waves recorded on the radial component. But actually, in the real world, we have the usual ZNE component. So we are going to rotate the usual vertical north, south, east, west components to a local coordinate, the ZRT component. So in this way, each wave type, the P wave, the SH, and SV, they can own their own component. So this rotation can eliminate the effects of source and repass, and it can always make sure the mean phase on its own components, avoiding the leakage of the strong mean phase into the weak converted phase. Okay, the deconvolution. As we know, the seismogram is a combination of source and the propagation effects. So after we have the data on 3 components, on the vertical, radial, and transverse component, we have the instrument response, and we have the source time function, which includes the near source and path. We also have the vertical response, radial response, and transverse response. So we make sure, so we have this vertical component simplification, which means in the vertical component, the P wave dominated. So we will make sure the IT convolve ST equals to the dVt. So in that way, the P receiver function equals to deconvolving the vertical component from radial component. And S receiver function, deconvolving the vertical component from the transverse component or the other component. Okay, so let's take a look at some real examples. This is a raw data recorded in the 3 component seismometer. On their Z component, the N component, and the E component. And we're gonna do the rotation and filtering and the deconvolution. After we do the rotation and filtering, we have this radial component, which meaning contains the SV energy. We then have this vertical component, which is dominated by P wave energy. After we do the deconvolution, we can obtain the radial receiver function, or we see the P receiver function. We have this direct P at time 0. We have this converted S wave from MOHO. And the time difference between the direct P and PS is around like 4 or 5 seconds. Sometimes it's 3 seconds. Okay, so we just talked about the direct P waves and the converted S waves from MOHO to the seismometer. But in addition to direct P waves and converted S waves, we also have crustal multiples. We can have PPPS, PPSS plus PSPS. So the lowercase and uppercase just show whether it's upgoing or downgoing. For example, the P wave went up to the surface and then reflect off the surface and then it can come back to the surface again. So we have direct P, converted waves, and crust multiples. And this is figure showing how they look like in the receiver function. We have direct P in time 0. We have converted S wave on around 4 to 5 seconds. We have crust multiples around 10 to 15 seconds and around 17 seconds or 18 seconds. Okay. Next, we can talk about some receiver function data from Alaska. So for the data we downloaded, they're from 2016 January to 2018 March, and we select earthquake with absolute distance between 30 degree and 90 degree. So for the events less than 30 degree cannot satisfy the general requirement for the P receiver function calculation, which require the near the vertical P wave repass. For the absolute distance larger than 90 degree, the P wave can propagate through the core mantle boundary, so the amplitude will be largely reduced. So that's why we choose epicenter distance between 30 and 90 degree. The magnitude cannot be too large, cannot be too small, so we choose larger than 5.5. At the beginning, we have more than 600 earthquakes and more than 100,000 traces. But after we do the data preprocessing and quality control, we finally have over 300 earthquakes and 20,000 traces, which is 20% of the original data recorded by 198 stations. Calculating and processing P receiver functions. We calculate each receiver function using the frequency-Endowment deconvolution. At that time, we use a FuncLab software to process the data to calculate the receiver function. We visually check all the receiver functions and only keep the traces with clear direct P arrivals and moho PS phases. And a total of 20,000 high-quality receiver functions are kept for further analysis. So we visually check all the receiver functions and only keep those traces with clear direct P and the moho PS phases, and of course the crust multiples. So next we'll take a look at some good examples and some bad examples. For example, for this one, this is one example from station AKSGA, and we can see this data is contaminated a lot, so we cannot use this for the receiver function. And another one is AKPNL. So the contamination could be caused by the seismometer, the set effects, calibration issue, or environmental conditions, such as weather or the ground movement. For example, I'm now in Oklahoma. If we have some stations in Oklahoma, then it can be largely affected by tornadoes. So that's some reasons about contaminated data. Another bad example for station AKFID, we can see in time 0, we see the polarity is opposite. So from my perspective, it could be largely caused by the instrument issue. Another example, too much noisy, low signal to noise ratio, so we'll pass this one as well. And this is a bad example showing the magnitude larger than around like 8.1, so it's larger than 8. So this is too noisy. We cannot use it as well. So we're gonna show some good examples for P receiver function. This is AKDOT. So after the deconvolution, we have very clear peaks at time 0. And we have around 4 seconds, we have converted S waves. Around 14 seconds, we have crust multiples, and around 19 seconds, we have PPSS and PSPS. So the black-green are the individual receiver function. And the red and blue means the stacked receiver function for all the individual receiver functions. So the blue dashed line here are the predicted travel time using the 1D velocity model from MOHO to surface. So we have this onset, P onset are fixed at time 0, and conversions clearly located around 5 seconds. Another good example for station TAL27K, we have very clear direct P and clear PS conversion. So these stations are located at clean and good spot in Alaska. So the data is really good. So for individual P receiver functions, the magnitude of the energy is relatively weak. That's why we're gonna do the stacking to have a robust signal. Okay, stacking by stations with move-out correction. So we will have many earthquakes from different directions. So from those different earthquakes, we'll have those real conversion points. But this station is located in this section, so the virtual conversion point should be over here. So we're gonna do the move-out correction to align all the phases properly before stacking, so the depths and velocity estimates are accurate. Otherwise, the phases arrival at different times due to varying rate parameters that can blur the final results. So the move-out correction is really important to adjust the delay time of PS conversions that are not beneath the stations. So based on time differences and also the known P wave velocity, we can have the MOHO depths. In this case, the MOHO depth is around 31 kilometer. Some good examples of stacked P receiver function. This one's for station TAH23K, which is located in a basin region of Central Alaska. So the black lines indicate the individual P receiver function. After stacking, it shows as the red line over here. We have this picked MOHO depths at around 32.5 kilometer. The velocity model we used in Alaska is ISP91. Okay, another example, TAE27K, located in northern Alaska in the North American Craton. Number of individual receiver functions, 31, and the red indicates the stacked receiver function. We have this peaked MOHO depths at around 31.4 kilometer. And then we'll talk about the HK stacking for individual stations. For this method, it assumes a 1D one-layer crustal model. So we have travel time for PS conversion. We have travel time for crustal multiples. And each equation contains crustal thickness and average VP-VS ratio of the crust. So based on these three equations, we can estimate both the crustal thickness and average VP-VS ratio. So we're stacking the amplitude at the predicted time for the conversion for the crustal multiples to have the optimal pair of H and VP-VS ratio. So the SH kappa here indicate the bright spot on the HK imaging. The omega-1, omega-2, omega-3 means the weighting factors for each phase. And the RT means the radial receiver function. So the H kappa image will be look like this. The horizontal axis is H. The vertical axis is kappa. So each line indicates the predicted arrival time for each phase. And the high amplitude indicates over here, shows the most possible H and K. Here is a synthetic receiver function on the right, and the HK stacking results in the left. So both primary converted phase, the PS, and the crust multiples are very clear and very clean. So they have comparable amplitudes because this is synthetic data. So it shows very clear the stacked amplitude for each phases on the HK imaging. But in the real situations, it's very hard to measure the arrival time on a single receiver function due to background noise. So we need to use multiple events to stack the receiver function to increase the signal to noise ratio. And we also need to do a lot of quality control to make sure we have clear PS, and hopefully we'll have identifiable crust multiples. So after we have the H and K, we can interpret. So the VPVS is sensitive to variations in rock composition, and the lower VPVS ratio, smaller than 1.7, is usually indicates the felsic rocks. The higher VPVS ratio, larger than 1.8, indicates more mafic rocks in the crust. So it represents the average value of a column of the crust from moho to surface. Here I show some examples in Alaska. From 1A to 3A are the result of receiver functions. Individual traces are gray, and the stacked receiver function are the red one. They all shows very clear on direct P and the clear PS conversion. Figures 1B to 3B shows the HK image results. So the color scale shows the stacked amplitude of PS, PPPS, and PPSS plus PSPS. So the white curve indicates the contribution from each phase. And the white dot in each figure shows the optimal pair of H and K, which is our result, showing the crustal thickness and the crust VPVS ratio. So we have, for example, we have 32.6 kilometer crustal thickness versus 1.78 VPS ratio for station TAF 25K. Okay, so we have this summation for the P receiver functions. P receiver function is a powerful tool to image the subsurface structures, and the time differences and amplitudes of the converted waves can give us some essential information about the depths, composition, and physical properties of layers below the seismometer. It's an easy way to invert for VS structure under a single station, and it's sensitive to gradients in VS. It's easy to be combined with other data sets for joint inversion of subsurface structure. You can use receiver function and surface waves to do the joint inversion. But there are some limitations as well. For example, it has information limited to a volume beneath a single station, is insensitive to absolute velocity. And the most important thing is for some complicated cases, such as anisotropy, some deepening layers, and non-uniqueness, it is very hard to explain the real Earth. Here are some selected references. So that's will be my talk. Thank you very much.
I have a question.
Okay.
First, I must say that was a very good talk. The first time I saw it, you really explained everything very clearly. My question is,
Okay.
if you compare receiver function estimates of crustal thickness with other seismic techniques, do they agree? Have you seen any comparison of like tomography, body wave tomography, or maybe active source active source seismic profiles. Is there good agreement between receiver function results and other results?
Yes, so for our receiver function studies in different regions, we always compare our results with other studies using either receiver functions or other methodologies, ambient noise or the body wave tomography. Most of them are agree very well, and the
Yes.
discrepancies are within like 2 or 3 kilometers for crustal thickness.
I think there was a question in the chat, whether you can determine the dip of the layer.
So for the H-kappa stacking method, it assumed the moho it assumed the moho is a flat moho, so it's a simple assumption. So for the dipping moho, we'll need to discuss. For example, we in the Indonesian or in the Fiji very complex region. If we use receiver function and H-kappa stacking, we always talk about, for example, the dipping layers, the anisotropy. What if this in the real world? What should we consider? Because HK and receiver function usually assume a very simple world, like 1D and flat layer, isotropic.
Right. And I think tomorrow you are going to show the results for Indonesia. Is that right?
Yes, tomorrow I'll show the results in Indonesia and Fiji.
Okay. What if there's a volcano? Can the receiver function work if there is a volcano? There could be partial melt in the crust. There should be some, maybe could be some molten. Is the receiver function still working near a volcano?
Yeah, in my studied regions, I always have stations near to the volcano, and for those stations, they have a very high VPVS ratio, usually larger than 1.8, 1.85.
Right.
Yeah, which correlate with the partial melting or the volcanoes. So this also gave us some great clues about what happened beneath the station or near to the station.
Yeah, the S wave becomes low S wave, so VPVS becomes high. I think
Yes.
I said enough. Maybe some other people. I will disappear. Congratulations, beautiful talk. I'll be quiet now.
Thank you. Thank you, Dr. Zhang. So maybe we start our discussion session. Maybe first we go to the Mr. Ahmad Abdul because I think he has some question. Mr. Ahmad Abdul, please.
Yes. Thank you, Miss, for your presentation. At first, I will ask about your first early slide. It's show that you model by using only earthquake show in mantle zone. Is it only limited for earthquake that's occur in the mantle zones, which is we know that some of the earthquake, big earthquake occur under 30 kilometers depth. Next is number 2, how to different the how you differentiate the conversion point of moho layers and other layers such as subducting plate maybe and other layers. And the third one is your results show it's list by back azimuth. So if you some side of the sensor, let's say the right one or the left one, have different structure than the other, north or south one. Did it will make the interpretation more challenging and the HK stacking, MoHo and VPVS model will be harder to interpret. Is it true or what?
Okay, thank you for your question. I think it's a very long question. So your question is, I only understand the last one. It is it is
Yeah, I can
difficult.
repeat here. The question is, can you use shallow earthquakes? What about earthquakes at a depth of 20 kilometer in a subduction zone? Can you
Oh.
use shallow earthquake for receiver function?
Actually, that's a great topic to if we have different earthquakes from different depths, how will it affect the receiver functions? Actually, I haven't noticed this category because when I download the earthquakes, I basically follow the epsilon distance criteria and the magnitude criteria, so I don't pay attention to the depths. But for example, if there's some very large magnitude earthquakes, so I don't think I'll choose those earthquakes because the magnitude will be very large, showing on the receiver functions. So at the beginning, when I process the raw data, I will pass that. So based on my experience, I usually have the earthquake between 5.5 and 7 magnitude, cannot be too large.
What about depth in this? What depth range are the earthquakes typically? Typical depth?
Intermediate.
Intermediate, like 200 kilometer, 300 kilometer.
Yeah, 50, 100, 150.
50, 100. Okay. Clean. The signal is more clean.
Actually, if we use some earthquake under the sensor, let's say it's we use teleseismic sensor, teleseismic earthquake in receiver function. But if we try to use, let's say, some earthquake under the sensors, let's say 300 kilometer under the sensor or more than that, is it possible to use receiver function?
You mean if the depth is more than 300 kilometer?
Yes, but it's not in the teleseismic criteria. It's just under the sensor or near the sensor, like that.
Local earthquake.
Yes, local earthquake.
Oh, it has to be the earthquakes from far away. So make sure for the P receiver function, make sure it's a vertical rate pass.
And to get the conversion, get good conversion of energy. So
Right.
another question he had is, how do you know it's the MOHO? It's all you know is a discontinuity. How you know it's really MOHO? It could be any boundary.
Yes, there are some in the crust. There may be some layers inside of the crust. So
Yeah.
in this situation, I would suggest we have more stations in this region so we can compare. For example, in a very small region, we have 2 or 3 stations, so we can compare the results. And sometimes we have a very clear maximum in the HK. For example, is 50 kilometers, 60 kilometers. That would be not the MOHO. So the MOHO
sometimes it's ambiguous. So occasionally it's ambiguous. There are 2 choices. There's a deep one and a shallower one, and you have to choose which one based on the other similar stations. The third question, number 3, was azimuthal dependence on the result. So an earthquake coming from Japan to Indonesia can look different than an earthquake coming from Tonga or coming from some other azimuth. How do you explain the azimuthal dependence of the result?
So in the receiver function, we have for each station, right? We have a lot of individual receiver function. So you can categorize the azimuthal for the receiver function. For example, 0 to 45, 45 to 180. So you can say if it has such effect.
Yeah, I heard a lecture recently where someone used the azimuthal dependence of receiver functions to determine something about the crust, but I forgot the detail. They took advantage of the different azimuth to because they could see that the amplitude of the converted phase was changing very much depending on the azimuth, back azimuth. Sometimes you can see the strong back azimuth dependence of the conversion phase.
Right. Yeah, so yeah, we can say sometimes we can say that azimuth variations in the receiver function. Yeah.
Yeah. Maybe there are more questions.
Yes. Dr. Zhang, this is question from Supriyatno.
Mhm.
Is the I'm sorry, is the anisotropy can influence the result?
Yes, because the HK stacking assume a isotropic layer. So if this is anisotropy, it cannot really explain the real world. So it's better to combine some other methodologies to conduct the research in this area.
Maybe this question for Dr. Benz. Hi, Dr. Benz. What are the challenges of implementing of if-MM in Indonesia? Is still here? I see. Maybe Dr. Benz is out. Okay, Dr. Zhang, I have question because like in the slide from Dr. Benz, give the Sumatra has intense for the larger earthquake, but when you show your figure, it's like the most intense about more than 5.5 magnitude. It's concentrate in the Sulawesi Islands or the Papua Island. Is it what happened in there between the Sumatra and Sulawesi? So why the most the larger what is it the largest earthquake and magnitude happened in the Sumatra and the intense ones occur in the Sulawesi?
Yeah, so the question is why the large earthquakes are occurring in Sumatra, but not occurring in Papua or Sulawesi or even magnitude 8.5 for Java. Maybe the time period is too short because we're only looking at 100 years of data, but the earthquake cycle is maybe 200 years or 400 years. For example, in Alaska, we had magnitude 9 earthquake in southern Alaska in 1964. But the repeat time for magnitude 9 earthquakes is 800 years. So you need to have a long time period to have the full picture. Geological processes are very slow. So maybe we don't have the full picture. We only have 100 years.
See.
So we'll be surprised. Maybe we can be surprised in the future. The pattern will change. Can change.
Dr. Monique, can you answer the question about what are the challenges of implementing if-M in Indonesia?
I think no challenge. I think only we just have to, we can provide the software and you can do it. I think finite fault modeling should be done in Indonesia, and you have very talented people. It has been done in many seismic networks around the world. So as long as you have good quality seismic data input, of course, it should be clean data. Everyone knows that the input data, the input seismograms have to be low noise and mostly clean data. That's maybe the biggest challenge.
I see.
We have another question. Ying, can you look in the chat?
Yeah, please. I think this a bit long question.
Okay, yeah, I can see the question. In the case of Alaska, what is the minimum signal noise ratio you are using? Can this use in Indonesia sensor? Any relationship between sensor misorientation with result of receiver function? If we have misorientation sensor less than 20 degree, the results are reliable. Okay. So I use different signal to noise ratio for when I'm pre-processing the raw data. For Alaska, because most of the stations in Alaska, especially in the northern part, is clean and quiet. So the signal noise ratio is 1.5. But in Indonesia, because it's really complex and tectonically active, so I applied a 2 for signal to noise ratio. So the signal noise ratio is based on the time window. It's pre-P wave and post-P wave. It's time window. So we calculate the time window, and we have that time window for signal to noise ratio larger than 1.5 or 2. We cannot hear you, Dr. Boni.
Thank you. I have the feeling that approximately half of the seismic stations in Indonesia cannot be used for receiver function. About 50% are too noisy, have poor signal to noise ratio. Or is it higher than 50% that are too noisy? What percent cannot be used?
40%, 40 to 50%.
40 or 50%, yeah. Okay, and that's a good answer. There's another question, relationship between sensor misorientation.
I think he correct his question because before his sensor below than 20 degree, but I think the right question is sensor greater than 20 degree.
Yeah.
Actually, I'm not very sure about this question. Can you sensor misorientation with?
I'm sorry, Dr. Muni, you are in unmute mode.
Every seismometer has an orientation, but in the field, maybe it's not so perfect. It's not north-south, it's 20%, more than 20% shifted. Is that a problem?
Oh, if the misorientation is not very large, I don't think it's a problem.
But
Unless it's
what percent?
I don't have a accurate percentage for that, but as long as it's not totally opposite, that should be fine.
Okay, all right. So it's not too sensitive to exact orientation. It doesn't need to be a 5 degree or 10 degree. It can be approximately correct. Yeah. Okay.
Hi everyone. If you have any questions, you can ask. You can raise your hand, or you can ask. Put your question in the chat box.
Okay, I have a question. Do you think it's possible to do a joint inversion for Indonesia with surface wave and receiver function so that the S-wave velocity is also determined, not only the MOHO depth, but also S-wave velocity? Or is Indonesia maybe too complicated for this? What do you think?
Yeah, I think someone already did the joint inversion using the receiver function and surface wave tomography. Yeah, so I think it's conductible.
Which paper was that? Rosalia? Do you remember the author?
I couldn't remember because there are a lot of papers.
Yeah. I think it was Bandung, ITB, Bandung people. Yeah. Okay.
So, yeah, we can do joint inversion in Indonesia.
That would be good.
Yeah.
So we can go to next talk if there's no more question.
Yeah, I think so. Maybe we can move to the next topic. And thank you for your participation. Thank you, Dr. Zhang.
Thank you.
Okay, for our next session, okay, we can give applause or react applause. Thank you, Dr. Zhang and Dr. Muni. And for our next session, we have Miss Ulfia Nur Sylvia from BMKG, who will present on assessment of noise. What is it? Acquisition data. Let's welcome her. Miss Ulfia, time is yours.
Yeah, thank you for the time, Rico. Okay, let me share my screen. Okay, can you see my screen?
Yes.
Okay. So, hello everyone, good morning in Indonesia time. Thank you for the opportunity that has been given to me to give the presentation and also discuss about this topic here in this training course. And let me introduce myself. My name is Ulfa Nur Sylvia, and I work in the Engineering Seismology Division, the Directorate of Engineering Seismology, Potential Geophysics, and Time Science. And in this precious time, I would like to present the materials about assessment of noise survey. And actually, this material has been delivered in the Global Seismology course 2025 in Japan by Hayashida Sensei. So I'm very glad to also share this topic in this training. So for our today's agenda are listed here. The first is about noise in general, and then I categorized by its source into seismic ambient noise and the instrument noise. Second is field survey about how to find a suitable location. And also I want to share about our noise survey during the global seismology training. And then we can discuss about the data processing using power spectral density. And the last is a conclusion. Okay, so first, what is noise? There are some definitions about this noise, such as in irregular fluctuations that accompany a transmitted signal, but is not the part of the signal. And from New Manual Seismology Observatory Practice book in the chapter 4, I think, noise defined as undesired components of ground motion that do not fit in our conceptual model of the signal under investigation. And so we can say that the noise is component which not categorized as a signal, and it can be disturb the signal recording. And from the left figure, we can identify the upper signal with the noise. And if we remove the noise, it becomes an original signal like the below one. But it doesn't mean that we cannot use the noise signal at all. In the other application, seismic noise can be used to investigate subsurface condition, like for short period is useful for microzonation studies, and for long period maybe for tomography studies. And this is noise classification by the source. Like we can see in the left figure, the natural noise can generated by the ocean microseismic, wind, and etc. It is in the low frequency, flow frequency, or the low period, and the noise can also come from man-made source vibration like industries, transportation, and maybe traffic. And also the noise can come from wave propagation in an inhomogeneous media like scattering, and usually called as the secondary signals. And also from gravity effects, such as Newtonian attractions of the atmosphere. the sensitivity of the sensor, or we called it the noise itself. It comes from magnetic field, temperature, and eccentric. And next, technical imperfection or deterioration of the sensors. That comes from corrosion, leakage currents, and eccentric, intrinsic self-noise of the seismographs, and also from the artifacts from the data processing. And for the first four bullets represent a proper seismic noise, and the four below is the real disturbing noise in the seismic records. And here, Wins in his research classified noise as this diagram to show the correlation between frequency in CPS, or now is known as hertz, and the pressure spectrum in the vertical axis. The key here identifies the component spectra, and the horizontal arrows here show the approximate frequency band of influence of the various sources. Okay, first let's talk about the seismic ambient noise. This type of noise is generated from the actual phenomena that occur daily, whether we realize it or not, such as ocean microseisms. And there are two characteristics of ocean microseisms. There are secondary and primary microseisms. The secondary microseisms generated by superposition of the ocean waves, where the ocean waves trains of the same frequency traveling in the opposite direction and they meet. And its frequency is double that of the ocean waves. And the second is primary microseisms are generated by the vertical pressure of wave energy or smashing surf on the shores. So it's only happen in the coastal, and the frequency is the same as the ocean waves itself. Okay. The next source of ambient noise is from sea bottom, where the noise level in sea bottom is much higher than inland and increases with higher frequencies. For broadband recording, frequency 5 up to 10 Hz is associated with breaking waves, while for the short period recording, frequency 0.5 until 5 Hz. Noise generated by small amplitude, high frequency of ocean waves that can be produced by light winds, and frequency 5 until 50 Hz associated with man-made sources. It's like ship traffic, marine mammal activity, and other machinery. Then for onland noise, the characteristic of long period recording can be associated with atmospheric pressure fluctuations and cause significant deformation below the surface. And for short period recording, generally it's associated with man-made activities such as traffic, industries, or even the transportation. And not only come from cultural noise, but it can also contain noise from natural phenomena like wind or water. This source recording coming from various directions, and the particle motion is uncertain. And the next is instrument noise, or we also called it self-noise. In seismic instrument refers to the unwanted vibration and signals generated by the seismometer and digitizer themselves, which can obscure the real seismic events. Sorry. So, as we know, recording process, what become the input is the ground motion. Then it will be produced in the observation system that involve like amplifier, transducer, or even integrator. So during this process, we're using the instrument, it always contains its own noise. And these are some sources from the instrument that will produce self noise. The first is flicker noise. exists in association with a direct current that caused by number of electrons in the device. And the second is a ripple noise in power supplies refer to unwanted AC voltage fluctuations that superimposed on the DC output and caused by incomplete separation of the AC waveform after switching processes. And the third is switching noise. It's generated by rapid switching actions of power electronic devices. It is like in switching power supplies, which can cause interference and affect the system performance. And then we have the thermal noise, or also known as Johnson noise, is a fundamental type of noise in electrical circuits caused by random thermal motion of charge carriers or electron within a conductor. And it can impact the performance of electromagnetic transducer. And the last is Brownian motion that affected when a seismic mass is small. It's approximately less than a few grams. And this noise can be neglected because the current seismometer observatory already have sufficient mass. The next chapter is field survey. First, we will know about site selection, including off-site survey and field survey and field studies, I mean. And for intermezzo, I want to show a glimpse of our noise survey during our global seismology training in Japan last month. Okay, so in selecting for permanent observation noise, we need to consider some factors to determine suitable location. The first thing to do is perform off-site survey where we can study maps and gather information about the potential sites from local and regional authorities. And we should prepare some information related to this condition, which shown on these points. The first is geological condition. This factor will influence both the seismic signal and the noise condition. And usually, the higher the acoustic impedance of the bedrock, and the smaller the seismic noise. And the most preferable site is solid basement rock to install the seismic station. And for topographic condition, it should consider about the extremely steep mountain slopes or deep valleys that may influence the seismic waveforms and signal amplitudes. Sites in moderately changing topography are preferable. And the next is about the accessibility, where the station which are too difficult to access are expensive to establish and maintain. We know that. And in consequence, they often suffer from inadequate maintenance and long repairs times. And for a distance from cultural noise, it refers to Wilmore 1979. And the fifth is future land structure and land ownership. It is very important to clarify the ownership of the land that being considered for a station installation and any plans for its future use because of the property ownership issues, or if it appears the development in the future, it will make the site unsuitable for a seismic station. And the last is we have to consider about the climate conditions, where we need to consider about a temperature of the site, wind speed, frequency of precipitation, lightning, and also flood possibility. Okay, for the distance from cultural noise factor, Wilmore 1979 gives this valuable information about the recommended distance and noise source in the general, like 16 kilometers from large waterfall or dams, 25 kilometers from power plants or rock crushing machinery, 15 kilometers from rivers, small waterfall or railways, 6 kilometers from highways, and 1 kilometer from small rock. And then it used as the minimum recommendation noise source to station site distances For the seismic station, Loma Palo Bonito assessment with the actual distances as shown at this table. And after we get the information from offsite survey, then field study is needed. And in general, there are some aspects that should people do in visiting the site. The first is verify the accessibility to the site. That station access should be generally be possible throughout the year. And to get the information about this availability, this can be checked by talking to the local people. And first to the geological condition, maybe the seismogeologist or the geologist should also verify the actual quality of bedrock as compared to the given in geologic maps. And it's also important to perform seismic noise measurement to know the noise level at the short term. At least it gives general overview about the site candidate. And the next is verify availability of power and telephone lines for the communication. And so this is the glimpse of what we have done in the last training where we did noise survey, which aimed to know the noise level by using 3 kinds of sensor, but I'm sorry, it's just 2 figures of the sensor. The first figure is broadband sensor, the second one is geophone, and the last one is accelerometer, but I'm sorry, I do not have the picture. And we conduct this survey into different locations in Mount Tsukuba. But unfortunately, we didn't have the result of this measurement to show in this time. So yeah, I'm very sorry for that. Okay, maybe we move to the noise data analysis using power spectral density, where this is the standard and widely used to characterize background noise conditions or to assess instrument performance. And this diagram shows the approximate amount of energy or power at the different frequency. And the most common procedure to compute seismic noise was established by Pedersen in 1993, who developed a global noise model which is now used at the global preference for broadband seismic or seismograph. And they define the new global height or NHNM and low noise models NLNM, which are currently the accepted standards for generally accepted limits of a seismic noise. And this is the example of the noise assessment using PSD in 3 different areas, which was conducted by Stutzman in continental, island, and the coastal area. We can see in the continental stations, they have lowest seismic noise in the whole period band, while for the island station have a long period greater than 20 seconds. Seismic noise level is similar to continental station, but noise level for the periods shorter than 20 seconds is much higher. Right. It is reflecting the fact that the island stations are more sensitive to the oceanic storms. And for coastal station, it has different type for each station, where some have a seismic noise level similar to continental station, and some have a high noise level. And to know the PSD or power spectral density, we can generate it from the IRIS web service in this attached link, and we can choose PSD or PDF, and then we can complete the requirement like network, station code, location, component, time, and maybe the output option. But it only provides data for station that belong to Global Seismic Network or GSN. And these are some results that we've been done using 2 different stations. in the training. First is GRFO in Germany, and the second is DAF station in Philippines. Based on this PSD plot, we can see that GRFO station has a better noise level, which still within low and high noise level, while in DAF station generally is past high noise level in the short period, and some data was high in the long period. It can be assumed that the cultural noise, which have the low period, caused this kind of plot, and for higher period, it means that secondary microseisms also affected the result. And when we checked the location, yeah, it's confirmed that the AF station located near urban area and close to the sea. And yeah, well, we can say that it matched. Okay, the next, if we want to analyze our own data, we can use OpSpy module called PPSD plot to plot the power spectral density. The right figure is the example of PSD from BMKG seismometer station. The upper one is body station, and the one below is PCGI station. From what I have got for body station, it is very logical to have such a plot shape, because if we can see at the signal, it is clear that this is not a good performance of the sensor. And while a PCGI station is in the normal condition and the PSG has high level in the secondary microseisms that may be caused by the ocean of superposition. Okay, from these materials, we can conclude that in the analysis of a seismic signal, it is necessary to identifying the difference between the signal under consideration and the noise in order to obtain appropriate results. And for assessing seismic noise in a recording, one common way that can be used is by using power spectral density, which can show the approximate amount of energy or power at different frequency that can be used to characterize background noise condition or to assess instrument performance. And this is my references for this presentation, and thank you for your time. And I back in the floor for the moderator. Thank you.
Thank you, Ms. Ulfa. Thank you for your good presentation. Anyone, do you have any question? Okay, maybe not yet. Okay, there is from Triubaya. If I need to obtain ambient noise from a sensor, how can I get it? And the second one is, how can I determine if the ambient noise I collected is of good quality? There is question from the chat box.
She's muted.
Say, Ulfa, you're mute.
Okay, thank you. Okay, from ambient noise from a sensor, we cannot get it. I used to discuss it with the speaker from my training course, that if we want to conduct the noise from the whole signal, because in the whole signal, we usually get we can remove instrument noise or other noise to get the appropriate signal. But if we want to have the noise itself and remove the original signal, we have to do some filtering, and maybe it will not in a good result. So the most efficient way, maybe we have to make the field survey with the maybe like the portable accelerometer or seismometer to get the ambient noise it depends on our study. And how can I determine if the ambient noise is collected is a good quality? So yeah, we can see at these signals and maybe we can also plot in the PSD if the signal is below the NH/NMR and above the NH/LM, maybe it's appropriate data to be analyzed. But if it's very noisy, maybe the curve will paces the new height noise model, and it may be not appropriate or not very present the local condition of the site. I think that's my point of view. Maybe from Muni, you have another response for this?
No, I agree with what
Okay.
you have said. Can we look at the list of criteria by Wilmore? You have a slide of, thank you. He suggested criteria, 60 kilometers from the dam, active dam. Yeah, okay, this is it. Yeah. So it seems that on the island of in Java, you'll have a hard time satisfying this because he suggests away from waterfalls, 25 kilometers from power plant, 15 from river, 6 from highway, 1. I think in Java you cannot satisfy. Okay, so that's just an observation. So now can we talk about the ocean noise, ocean bottom noise, seafloor?
Yes.
Okay, this was very interesting. All of your talk was very interesting, but this was very interesting. Noise level in sea bottom is much higher than in land. Really? Does that mean near the shore or deep water, deep ocean, or any place or any part of ocean?
For this part, I think it's from the deep water because I get this reference from Mason 2017. So maybe for sea bottom, I think it's the low in the this insulate in the seafloor.
Yeah, this is new. I didn't realize this, that the sea bottom noise level in the sea bottom is much higher than land and increases with high frequency. That's I would have thought the noise level in the sea bottom would be lower, and I'll have to try to learn more about that, why it should be quieter. Can we look at your slide for the criteria? You have 6 or 7 criteria in the beginning of your talk.
Okay.
Like accessibility, beginning with accessibility.
For the site survey, site selection like this.
Okay, so pardon me, but in my humble opinion, the most important criteria is missing here, and that is security. Security.
Oh yeah. Yeah.
Problem we have in
That's
North America is that people are disturbing the instrument.
Yeah, that's also the important thing. Okay, thank you, Moni, for the additional
And as you know,
information.
usually the geophysicists they will choose the most secure site. They will not worry too much about noise from cultural or land ownership or climate. They try to go for security, where they can put the station and it will not be stolen.
Yes.
Thank you very much for your lecture. Very informative.
Thank you, Moni, for your additional knowledge information to complete my presentation.
Welcome.
Miss Nova, there is so many questions, so maybe we can move to second question. So we cannot get the good quality of the ambient noise only using broadband sensors.
Oh, okay. from who we can put the
Tri
sensor.
Ubaya.
Yeah. Actually I do not have a clear answer because I haven't done this survey. But as my discussion about this topic with our lecture in the training, it's probably it cannot clear. We cannot get the clear ambient noise from it by using broadband sensors, I think.
Okay.
Sorry, please correct me. Anyone?
Okay. Please Nihlu Desi.
Hello, I'm sorry. My video is off because the sound will be bad if I turn on the video. I want to ask, for example, to Miss Ulfa. Thank you for the nice presentation. As you said before, there are many categories of site selections. For example, is distance from noise. And then, but in many area, as we know, most of seismic sensor in Indonesia was installed many years ago. For example, for the first, this sensor was installed located in a remote area, but as the time changes, the area then become an urban area. So if we compare the PSD value of the sensor will be different then and now. Then how do we anticipate this? Or is there any method or field that can be applied to the data to make sure the data quality is still good?
Okay, to make sure it, yeah, again, the most common way is using the power spectral density. We have to plot the energy that comes from the recording. But the other way is to do the filtering if we want to correct the noise, the signal that we want to analyze. I think it's that kind of the thing that we can do.
Okay, thank you. Maybe one question before we start. We continue to our next session. Maybe for the last, for the last two question, we can drop in the discussion session. And Ms. Ulfa from the Rahman, according to your perspective on slide number 11, how do variance in shallow depth lithology and moderate topographic change affect seismic wave propagation, sensor stability, and data quality? Additionally, what are the best method to address this challenge?
Okay, how do so for these questions, I think I don't really get how we can face this challenge because how the topographic can change the effect of seismic wave propagation, but maybe it will affected by the wind that came across the valley, and also it can affect the signal recording. I think that's the theory. And for the best method, I'm sorry, I cannot answer this one because I'm still have no experience in the installing the seismic station.
Okay. I think we have to finish all the questions. So after that we can move to the next session. Finish the questions. Yeah, Ms. Ulfa, the next question is is it okay, right?
Okay.
Okay, whether the standard limit maximum and the minimum on PSD can be applied to all conditions in Indonesia. Should each occasion have its own boundaries?
In general, I think for PSD, it's just measure the seismic in general. The seismic in Indonesia, I think in Indonesia and or the other country, I think it's the same frequency. Like motorcycles, we have how many frequency, how high the frequency is. The origin macro seismic, how how much the frequency is. I think it's the same for all the region, and yeah, it can confirm that we can use the PSD level at the all the region. Because it's just measuring the noise and not according by the geological condition or by what. It's just the noise itself.
That
I think
question.
it's that.
In the PS checking area. Checking criteria.
I'm sorry?
The not the last. Can
Oh, okay, okay.
are too noisy, so that it can be included in the qualification.
For PSD checking criteria, I think we have to I think PSD is aimed to know whether our data is good or not. So it has to be that its own original seismic recording, not by filtering or what at first, because we want to know that is it original is good or not. If we know that our signal is not good and interference with many noise, we can do that filtering in the second step to get the better quality of the signal.
Okay, thank you. And I think this is your last question. Does site amplification associate with noise, and how big contribution to give inaccurate earthquake parameter?
Okay. It's a quite hard question, I think. But as I know, yeah, we know the HVSR method, right? Horizontal to vertical spectral ratio. It uses noise too, and it shows that there are amplification noise from the HVSR analysis. But as I know, that is the not original amplification factor of the ground. It's just the maximum amplitude, I think. But I don't really know whether it is a good or a suitable factor to get the amplification or not. There are so many research about this and so many this we cannot use that anymore. Maybe for the forget the amplification factor that represent the actual condition of the site. And we contribute to give any so for the how big contribution, I think it's very if the noise level is very low, I think the earthquake analysis or especially in the earthquake parameter that will be analyzed to the earthquake parameter, it's maybe will be very good data to get the suitable parameter of the earthquake if the sensor of if the recording has low noise. I think that's my opinion for this question.
Thank you, Ms. Ulfa.
Okay.
I think there is no question more, and I think we can move to the next session. And
the
now,
last question.
oh, which one?
Well, if indeed the noise from instrument is not from nature,
Oh, yes,
does the instrument need to be calibrated or relocated?
I don't know. Okay.
Oh, from the instrument that comes from its instrumentation, we can remove the noise instrument. I think what I mean about the noise instrument. And if the sensor was very broke and have the high noise level, and maybe it cannot be cleared by the what is called removed instrument, so we have to fix the sensor and do the calibration, yeah, as he said in the checkbox. For relocated, I think it depends on the noise level in the surrounded area. And I think I want to clarify the Pak Tri Ubaya question. So we cannot get good quality of ambient noise only using broadband sensor. I think if our aim or our goals is to get the noise itself, so we can so maybe we can conduct the noise survey by a broadband sensor. I think it also can it also can to analyze the ambient noise, get the ambient noise from the broadband sensors. Yeah, it's up to the goals what we want to get from the survey. Thank you,
Thank
Mr.
you. Yeah, thank you, Miss Ulfa.
Thank you.
I think there's no question more. Should we move on to the next topic? I think so. Thank you, Miss Ulfa. And our next session is cover Unix basic for seismic observation and will be presented by Mr. Jambari from BMKG. Please welcome him. Mr. Jambari, time is yours.
Okay, Mr. Rico, thank you so much for the time you given to me. And I would like to introduce myself. My name is Jambari. I'm a station operator at the Jayapura Geophysical Station. Can I share the my slideshow?
Yes, please.
Okay, in this session, I would like to talk about basic Unix. Some of you might be already familiar with the term Unix or Linux, but I think Linux is more familiar than the Unix. But without further ado, let's deep dive into this topic. And for precaution, some of you might have a better understanding in this kind of topic, and I'm not expert into this topic. So if you find some incorrect terms in the explanation along the lecture, you can immediately interrupt me immediately, and we can discuss together. Here's the outline. The first one is I'm going to talk about the history, and then the advantages, and the third one is Unix commands, and the last one is notable software that used for the seismic observation in Unix. Why is Unix important? Unix is very important because it is pretty much responsible for computer as we know them today. And in terms of performance, Unix provides CLI, command line interface, and the CLI operate through text-based command. This directing all processing power to task at hand and resulting in the high efficiency and precision. You know, you might be familiar with this picture, right? This is a game, PS5. Previously, I said that Unix is responsible to the current state of computers development, and PS5 is also inspired by Unix. And our Android and iPhone both inspired by Unix. As we know, these two smartphone operating systems are our daily drivers. And you also know that, and even the firmware on our home roller is ultimately influenced by Unix. So Unix is like the grandparent of all modern day OSs. And an OS being the operating system, and operating system is the middleman between the physical hardware we can touch and the digital software that we use. So it's the backbone of our computing needs. Now is jump into the unique history, and so in this regard, it is really hard to fully appreciate how important it is. So, but I want to do it right. So what we are gonna do is to go way back to the very beginning, the 1960s, on ancient times when punch cards were still being used for computing. The discal wasn't even a thing yet, and actually unique wasn't even a thing yet. Initially, we're going to start with something called Multics, which was a failed attempt at an operating system. And the only reason why I'm talking about it is because it created an important spark. Because a guy who worked on the project, a guy named N. Thompson, he would go on to create Phoenix out of the ashes of Multics. You see in this figure Ken Thompson in 2019, and then the Dennis Ritchie in May 2011. In 1970, Ken Thompson he put together a team to make new operating system, and this is basically they want to get rid of all the complication of Multics and make it work right. They call this new operating system Unix. That's Unix with a C, not an X, and it was changed to an X later. But one of the reasons they called it Unix is because there was a joke. It was a castrated version of Multics operating system. So okay, a few years after they making Unix with a C, UNICS with they're making developments, whether they're making new versions or they're updating it, but it was the first version where everything changed. One of the programmer on the project, guy named Dennis Ritchie, he created the C programming language. It is insane when we think about it. He created a programming language, but anyway, he made it for version 4, and it changed everything because from that point on, Unix could be ported to a variety of different system and hardware. Because basically it's a genie taken out of a bottle and could not be put back. And this and in this you can see in this figure this tree right here is the result. We have complicated hierarchy of operating system versions, or relating back to that initial Unix release. So you can see right here where C was implemented in the version 4. There were some major branches that started to form. You on the left side, you have the BSD branch, which is what they work on at UC Berkeley. And if you follow it down, you have next step, and ultimately you can see below the next step, we have Mac OS X. So Mac is actually a derivative of Unix. So you might be using Mac right now, not even knowing that you are kind of using Unix. And back to the tree, on the other side of it, even Microsoft has an entry on this tree with Xenix. But as you know, they went on to ultimately create an entirely separate tree of their own, starting with MS-DOS, and then they have Windows as we use today. But I just want to be clear that Windows is not related to the original Unix, even though Microsoft has a Unix version on this tree. Uh, Windows is structured very differently. It is not Unix-like. But an operating system that Unix-like is Linux. Yes, Linux is not Unix, and actually a core part of Linux is GNU, and that literally stands for GNU is not Unix. So Linux is not Unix, but it is Unix-like because what that means is it's not direct descendant of the original Unix, but it embodies the same field. As you can see in the figure, uh, there are three colors: pink, which is a closed sort, and then that means the code is closed off. You can view it. You cannot edit it. You are not allowed to or even to track it. Then we have open source in green color, which you may be familiar with the term. The code is in because the code is openly viewable. You can change it, track it, make your own versions, try things out. And then there is yellow that makes shared some type of operating system. Uh, there's global consortium called the Open Group. They own the trademark of for Unix in order for you to call your operating system Unix if you make an OS, and you want to be certified. You have to pay a lot of money. You have to go through a lot of testing. You have to comply with a bunch of regulations and standards, and it's a complicated process. And so there's money involved. Also, it's not very free software. So we have another term that there's true Unix. We've been certified as a true Unix operating system, and then we have Unix-like operating system. So there is two terms. The first one is a true Unix, and then another one is a Unix-like operating system, which are compatible with the Unix standard. They implement things correctly, but they haven't been certified as actually true Unix. And this is because of financial considerations or ethical objections to the existence of the idea of a true Unix. So Linux is not considered true Unix, but rather it's considered Unix-like. Uh, you remember that Linux itself is just a kernel, which is very, very important. Again, that the piece of the operating system that connect the hardware to the software. So what Linux really is the kernel. But when we think about like Ubuntu, what Ubuntu is Linux distributions. It is one of many distributions out there. There are nearly 1,000. You may heard of Fedora, Slackware, Debian, CentOS, or Mint, or open source, and the Ubuntu that we will be using, and what its distribution is. So the distribution is it's a Linux kernel. It has some GNU tools, documentations, package manager, desktop environment, window management system, and a whole bunch of other things combined to form a full operating system. Now we have one last piece of terminology and history and all that stuff to get out of the way before we move on to actually running commands. We need to talk about the term shell. So you may have heard of this before. If you're on Windows, you may have heard of the PowerShell. You may have heard of Bash or Z shell, ZH, or you may be never heard of them, but it's okay. But there's this concept of something called shell. What the shell is, a very important piece of software that is going to expose the operating system itself to human users or to other program. So it's the thing that takes our commands and hands them over to the operating system to actually perform. And the term shell comes from the fact that it's the outer layer around the operating system, like the shell around the oyster. So there is other terminal. Way back in the day, terminal used to be an actual piece of hardware. It would have a screen and a physical device with a keyboard. You'd go over and you enter your commands into the terminal. Today, terminal just a piece of software. It's an application. There's many different terminal applications. It's a place where we go to type our commands. We hit enter, and there's some shell that we are using in the terminal window. By default on Ubuntu and most Linux distributions, that shell called Bash. On a Mac these days, the shell is called G shell or GSA. And again, their job is to take commands that we provide or other applications, then give them over to the operating system and make sense of it all. So I'm gonna using Bash as the default shell that comes with Ubuntu in this session for practice, for exercise. And then here comes the question, why using Unix or Linux? Why this matters, and why should we master the command line? At times, it might seem like you are now running stuff straight out of the 1980s movie, right? But we're far more advanced and things have improved so much. Why do we still have to use text commands? Well, there's a bunch of reasons, including the fact that you can do a lot more from the terminal using commands. You'll have more control, greater access. You can do things you just cannot do otherwise. There's just no way around that if you want to start a server, manage different processes, interact with databases, waveform inversion and analysis, tsunami modeling that need high performance and stable operating system, and all sort of things like permissions, file permissions. You need to know terminal command to do that. Another reason, it's faster, at least once we pass the basic hurdles. When we learn the commands, we will get used to them. You can do things way faster. We can make like 10,000 files in a single line, and I can make 10,000 empty files, all with different names. If we're doing that graphically with mouse or file as in the Windows as other operating system, like using graphical interface, click a new save file, it will take hours. Now, so that's just sort of for a factual example, but in general, we can do things much faster using the command line or Unix. The problem is when we're learning, it's going to be much slower. I kind of already hinted at this one, but we can actually automate things. We can speed up repetitive processes. We can save ourselves a lot of time. And another reason, it's available everywhere. So if you learn these commands, you'll be will be able to work on any Linux distributions. We'll be able to then switch over to Mac if needed and use the commands on a Mac, because Mac is Unix and the command line is the same. But now on Windows, it's a little bit different. So it's not technically available everywhere, but these commands we're going to learn are pretty standard across any sort of developer, and which actually it's essentially a requirement for whatever type of coding related. We need the command line. So we will have tools that only access on the command line. It's just part of the expected skill set. And if you are a Windows user, if we are Windows users, let's talk about the WSL, Windows Subsystem for Linux. The problem here on Windows, we just don't have access to the same commands. They're implemented differently. Windows is not part of the Unix family. This Unix likes or the Unix like operating system. So this means that a lot of commands we will learn are not going to work on Windows. So they work differently, or they will work partially work. Uh, Now, Windows has its own set of commands, and as you could uh, live in the world exclusively, Windows is just a different world. So, if we want to a lot of the common developer tools, and we need to get some way of running Linux command on Windows. Uh, the way that we do this is really there were two options. There used to be one. We used to have virtual machines like Sequin, but it's too paid to install. It's totally isolated from our actual Windows operating system, and it can be slow, and it can have a lot of overhead. And uh, now we can have really cool fancy option called WSL, or Windows Subsystem Linux. This is actually put out by Microsoft and Canonical. Canonical is the creator of Ubuntu, and it allows us to run a Linux environment directly on Windows or inside Windows. So it's not isolated. And it's not a virtual machine. It's actually work directly inside Windows. It's just command line version of Linux, to be clear. So we're gonna have separate desktop. We're gonna have, all the apps. We're not gonna have all the apps and like the Ubuntu desktop. But uh, the point is we can be a Windows user and have Linux command from the command line. So it's really really cool. It's also updated pretty frequently and still under active development. And the really good news is that it's a lot easier to install these days. So I'm gonna practice a little bit how to install Windows subsystem Linux Ubuntu.
Thank, thank you.
I want to share. Uh, uh, what is it? How can I share all the computers? This one. Here, we can open in the Microsoft Store, and then we just type Ubuntu, and I think, and it will display a lot of Ubuntu versions, such as Ubuntu, which is the default, will be 24. The present version of Ubuntu. And then also there's Ubuntu 22.4 or Ubuntu and Ubuntu 20 and Ubuntu 18. So we just need to press open and then install, just like that. Or we also can install through the command window. If you want to install the Ubuntu in this through WSL, there's a requirement, which is the Windows 10 version 2024 with higher build number is 19,041 or higher, or Windows 11. We just running this command in the command window WSL install, and it will be directly install the Ubuntu with the default version is 24.4 or long-term service. Now I'm gonna run my I already installed some of this Ubuntu. As this. To select this, just as usual terminal. To select your Ubuntu terminal, you can type any Unix command such as ls. I wanna, for example, let's just practice some command. For example, pvg. This basically just like a Ubuntu terminal, but only just terminal. There's no GUI. And we'll try learn to the command pwg, which is the to showing the current working directory. So if you type pwd, you should see a directory path print out. There are a couple of basic to understand here before we get into the detail of what the command actually did. First is that when we type a command, it appears on the same line as the alt text, and then the text is here to tell the computer to ready to accept a command. So there are a lot of basic command. We can mkdir, make directory. And this is, and we can change directory to the previously directory that we made. What did I do wrong? Yeah, currently we're in the we just make a directory that I already just did. So this is basically just pure like the original version of the Ubuntu. We can see the structure of the file system. As you can see, there's a home, bin, gif, let's say, and media, up, and for just like actual Ubuntu. And we can move when we work in this terminal, we can move the result of files to Windows. The Windows file system is in the folder mnt. There's a Windows directory I can see. We can also even list it. Yeah, so we can benefit from the straightforward graphical user interface Windows, which is we get familiar with it, and also use the powerful of command line. We can even install just like geophysic seismic applications such as SAP. For example, you can we read this file. I don't know if you see the result or not. Let's move on into the next presentation. Here are some of the top 50 Linux commands that we need to know, and it is already widely available in the internet. And I want to share about the notable Linux software for seismic data processing versus SAC that I already installed. You can install it in the Ubuntu under the Windows subsystem Linux. So I think we already all familiar with this kind of software. SAC is a widely used software for analyzing and processing seismic waveform data. It was originally developed at Lawrence Livermore National Laboratory and is now maintained by RIS. SAC is commonly used by seismologists for tasks such as key feature of SAC, waveform visualization, signal processing, event detection, seismic data format handling, batch processing, integration with other tools. We also have Seiscom. If you want to just for practice, you also can install it on this WSL. Anything software that can run through the terminal, even Python and OpSpy, we can run it through install it through this Ubuntu under Windows subsystem Linux. Okay, Mr. Rico, I think that's from me, from my session.
Thank you, Mr. Jambari. Everyone, do you have any question about this topic? So we can do discussion. If you have any question for Miss Ulfa also, you can ask here.
I have a question, simple question. If you have a problem with the operating system, how can you get technical support for Unix? Technical support, how is that available?
For Unix, there's a documentation page for the Unix that's widely available in the website. But for Unix, that we need to pay the license, so it's quite there will be supporting system or usually there's a customer service for the paid Unix system. But if you want to debug yourself, you can find widely in the documentation of its distribution of the distro of Unix, because Unix is paid versions. So people usually tend to use Linux because it's cheap and it's open source, and there's a lot of supporting system to do that. I think that's from me, Mr. Moon. If you have any insights, you can add to the discussion.
And recently, the computers went from 32-bit to 64-bit. Well, not so recently, but computers are constantly upgrading. How are these operating systems able to keep up with rapid improvements in computation in the hardware side?
Yeah, that's why the important is we need to choose when we want to install some operating system, we need to choose the version of the operating system. There are such as the Ubuntu long-term services or any other kind of operating system. They usually display the how many years there's going to be the developer going to support for the operating system. So if we change however, even though the software from 32-bit to 64-bit is rapidly changing, the developer is going to be handle that, because if we choose the installation of the operating system is the support for the year. So such as for example, the Ubuntu Rotom system, there will be displayed this operating system going to be support to up to 2030 or 2024. So we probably can be safe to choose. We don't need to mind regarding the 32 or 64 bits, because developers support it, and we will be constantly update the either the kernel or the other packages.
Thank you. Anyone, do you have any question? Maybe from me, Mr. Jambari, what is the most advantage from the Unix like for what is it? For seismic observation. Yeah. What is the most advantage? Right. And if you have any recommendation, which Unix like do you prefer? Like, okay, I think the Ubuntu is the best for the seismic observation, or another one.
Actually depend on our project. For example, if we need to further analysis such as instrument response or filtering, such as we can using SAC or OpSpy that's currently popular, which is also available in Linux or Unix, and for waveform retrieving and then instant analysis or real-time analysis, we can use SESCOM or another tools. There's also another waveform analysis such as GL2. So we can choose which one. But I think it depends on the project that or the result that we need, and which is best distribution that we can choose. Probably we need to start from the familiarity. The first one is the command line and the environment, because each distribution has different package manager, such as, and also the number of supported application of or dependency also or different distributions. So it also back to the project that we're gonna use, but mostly for basic such as a server, most distribution support networking. Most distribution has its feature and has strong in its because network or data analysis of high performance is the key point of using Linux or Unix.
I see. Thank you so much. Anyone, do you have any question? I think there is no question more. Thank you, Mr. Jambari, and thank you, Dr. Muni,
You're
for
welcome.
attend this day. And thank you all for your engaged discussion. This concludes our session for today. We truly appreciate your active participation and valuable insight. And before we end, we would like to remind you that our training will be continued tomorrow at 9 local time or Western Indonesia time or 2 UTC. We encourage you to join us again. And once again, thank you your participation and contribution. Have a great day and see you tomorrow. Thank you.
Bye-bye. Bye, everyone.
Thank you, Mr. Muni.
Very good lectures. Thank you very much.
Thank you very much.
Mungkin nanti malam dulu ya.
And don't forget to fill the attendance form. Di Los Angeles there.